After Pro.
Hi guys. For this video I will discuss more complex electrical circuits compared to the previous videos, which contains more than one voltage source. In solving that kind of circuit, we are going to use network theorems and laws. The first one will be Kirchhoff's law by Gustav Kirchhoff. There are two simple laws expressed in this law. By the way guys, examples are discussed at the end of the video. So make sure to finish watching so it will help you to fully understand the topic. And also guys, please make sure to like, share and subscribe for more videos. So now, we go for number 1. The current law. The algebraic sum of the currents at any junction of an electric circuit is equal to 0. We can also say that the current entering a junction is equal to the sum of current leaving. By using that law we can rewrite the example circuit to a current equation as I sub t minus I sub 1 minus I sub 2 minus I sub 3, which is equal to 0. Then the number 2 is the voltage law. The algebraic sum of the EMFs and the resistance voltage in any continuous path of an electric circuit is 0. So as an example, taking the loop A B C D E F A, we will have the voltage equation E sub A minus I sub A times R sub A plus I sub B times R sub B minus E sub B equal to 0. In the two laws, current law and voltage law, the term algebraic refers to the arbitrary assumed signs plus or minus given to indicate current directions, EMFs and resistance voltages. Guys, you have to take note of 3 quantities used in this law. We have the current represented by positive I or negative I. The voltages or sources of EMFs like generators or batteries represented by positive E or negative E. And the resistance voltages involving the products of current and resistance represented by positive I times R or negative I times R. Guys, you also have to take note before writing the equation. To properly identify all current directions and EMF's polarities, let's say that the algebraic plus is denoted by a current to a junction or a potential rise in passing through a source of EMFs or a resistor, while algebraic minus is denoted by a current away from a junction or a potential drop in passing through a source of EMFs or a resistor. To properly illustrate the application of Kirchhoff's law, here is an example. As you can see guys in the example that there are 2 sources, and the resistors connected are more complex compared to the other given examples in the other videos. In solving this kind of circuit guys, you have to assume the direction of current through the 6 resistors. The direction may or may not be correct. So if the yield answer is negative, then the assumed direction is incorrect. You just have to reverse the direction of your assumed current direction. Later, you will see in examples like this. Conventionally the direction of current through the battery is from negative to positive polarity. Next, after we assume the direction of current or the polarity, we have to indicate junctions or points in the circuit. Right after that, we can now write the current equations. Now we apply the current law. Current entering a junction is equal to the sum of current leaving the junction. So at junction M, I sub A minus I sub D minus I sub F, which is equal to 0, or I sub A is equal to I sub D plus I sub F. As you can see guys, at point M, the entering the junction is I sub A, which is positive, while I sub D and I sub F are leaving the junction is negative. Adding all the currents considering the polarity, we will have I sub A minus I sub D minus I sub F equal to 0. Since the current law is the algebraic sum of the current at any junction of an electric circuit, which is equal to 0. After the current equation is written, then we go now for the voltage equation. Okay, for loop AMNQA, we have E sub a minus I sub a times R sub a minus I sub d times R sub d minus I sub c times R sub c equal to 0. As you can see, guys, for the loop AMNQA, E sub a is positive while voltage drops across the resistor of the loop is negative. For loop BPNQB, sub b minus I sub b times R sub b minus I sub e times R sub e minus I sub c times R sub c equal to 0. Also for the loop BPNQB, E sub b is positive while the voltage drops across the resistor of the loop is negative. To easily write the equation, guys, we just have to take note of the polarity of the voltage and voltage drops we assumed in the circuit. For loop AMFPBQA, we have E sub a minus I sub a times R sub a minus I sub f times R sub f minus E sub b plus I sub b times R sub b equal to 0. In this loop, we just have to consider the ending polarity of EMF and voltage drops across the loop. For E sub a, the ending polarity is positive, so it will be written as positive E sub a, or simply E sub a. For I sub a times R sub a, the polarity is negative since the ending polarity here is negative, so it will be written as negative or minus I sub a times R sub a. Same also with I sub f times R sub f, the polarity is also negative since ending polarity is also negative. So it follows, it will be written as negative I sub f times R sub f. But for I sub b times R sub b, which ending polarity is positive, so it will be written as positive I sub b times R sub b. And for the source E sub b, the ending polarity with respect to the loop AMFPBQA is negative. So the equation, guys, is written as E sub a minus I sub a times R sub a minus I sub f times R sub f plus I sub b times R sub b minus E sub b. So we go now for several examples. For example number 1. A circuit in which two sources E sub a and E sub b deliver current to a load resistor R sub L. Through line resistors R sub a and R sub b. R sub a and R sub b are internal resistance of the two sources. So the circuit will be like this. So calculate for A, I sub a, I sub b and I sub L. B, the load voltage V sub L. C, the power P sub L which is delivered to the load. The solutions, guys. At junction E, we have I sub a plus I sub b minus I sub L is equal to 0. Which can also be written as I sub a plus I sub b equal to I sub L. Which will be our equation number 1. For loop AFEDCBA, E sub a minus I sub a times R sub a plus I sub b times R sub b minus E sub b equal to 0. Substituting the values. 24 minus 0.4 I sub a plus 0.4 I sub b minus 26 equal to 0. Simplifying, we have 0.4 I sub a plus 0.4 I sub b minus 2 equal to 0. Which can be written as I sub b is equal to 5 plus I sub a. It will be our equation number 2. Next is the loop AFEBA. We have E sub a minus I sub a times R sub a minus I sub L times R sub L equal to 0. Substituting the values. We have 24 minus 0.4 I sub a minus 0.8 I sub L equal to 0. This will be our equation number 3. By substituting equation number 1 to number 3, it will be 24 minus 0.4 I sub a minus 0.8 multiplied by open parenthesis I sub a, and I sub b close parenthesis, equal to 0. Simplifying the equation we have 24 minus 1.2 I sub a, minus 0.8 I sub b, equal to 0. And this will be our equation number 4. Using equation number 2 and number 4, we will have 24 minus 1.2 I sub a, minus 0.8 times open parenthesis 5 plus I sub a, close parenthesis, equal to 0. Then it will become 24 minus 1.2 I sub a, minus 4, minus 0.8 I sub a, equal to 0. Then the result will be that I sub a will be equal to 10 amperes. Using the value of I sub a to equation number 2. I sub b is equal to 5 plus 10, which will result in 15 amperes. So to solve for I sub L we have I sub L is equal to I sub a plus I sub b. So with solved values we have I sub L is equal to 10 amperes plus 15 amperes. So I sub L is equal to 25 amperes. Then to solve for V sub L, simply I sub L times R sub L. V sub L is equal to 25 times 0.8, which will result in 20 volts. And lastly for the P sub L, which is equal to I sub L squared times R sub L. Substituting the values, we will have 25 squared times 0.8 ohms. So P sub L is equal to 500 watts. Okay guys. We go now for the number 2 example. A DC generator is connected to 2 storage batteries which are connected in parallel so that the latter will be charged. The open circuit voltage of the 2 batteries are E sub A, which will be equal to 108 volts, and E sub B, which is equal to 110 volts. The internal resistance of the batteries are indicated in the circuit, and as well as the internal resistance of the DC generator. So calculate for I sub A, I sub B and I. For B, the total power delivered by the generator. For C, the total power loss in the resistors. For D, the efficiency of the system. The polarity of the generator and current flow are indicated here. So the solution guys. First we have to write the current equation. So I will be equal to I sub A, plus I sub B, which will be our equation number 1. Then next we have to write the voltage equation. E sub G, minus I times R, minus I sub A, times R sub A, minus E sub A, which is equal to 0. Substituting the values of equation and the values of the resistors to this equation, we will have 122 minus quantity I sub A, plus I sub B times 0.15, minus I sub A, times 0.5, minus 108, equal to 0. Simplifying. 14 minus 0.15 times I sub A, minus 0.15 times I sub B, minus 0.5 times I sub A, equal to 0. 14 minus 0.65 times I sub A, minus 0.15 I sub B, equal to 0. Equating it to I sub A. So negative 0.65 I sub A, equal to 0.15 I sub B minus 14. I sub A is equal to 14 minus 0.15 I sub B all over 0.65. It will be our equation number 2. Writing the voltage equation from E sub B. E sub G, minus I times R, minus I sub B R sub B, minus E sub B, equal to 0. So we have 122 minus 0.15 quantity I sub A, plus I sub B, minus 0.25 I sub B, minus 110, equal to 0. 12 minus 0.15 I sub A, minus 0.15 I sub B, minus 0.25 I sub B, equal to 0. 12 minus 0.15 I sub A, minus 0.4 I sub B, equal to 0. Equating it to I sub A. Negative 0.15 I sub A, equal to negative 12 plus 0.4 I sub b. So I sub a, equal to 12 minus 0.4 I sub b all over 0.15. It will be our equation number 3. Using the equation number 2 and 3, we will have 14 minus 0.15 I sub b all over 0.65 equal to 12 minus 0.4 I sub b all over 0.15. So I sub b is equal to 24 amperes. Using the equation number 3 and the value of I sub b, I sub a is equal to 12 minus 0.4 I sub b all over 0.15. So 12 minus 0.4 times 24 all over 0.15 will be equal to 16 amperes. I, which is equal to I sub a, plus I sub b. Therefore, I is equal to 16 plus 24, which will be equal to 40 amperes. We can now solve for the power delivered by the generator. P sub g is equal to E sub g times I. So P sub g is equal to 122 times 40. That will result in 4,880 watts or 4.88 kilowatts. For the total power loss, loss is equal to I squared times R plus I sub a squared times R sub a plus I sub b squared times R sub b. Substituting the values, we have 40 squared times 0.15 plus 16 squared times 0.5 plus 24 squared times 0.25, which will result in 512 watts. And for the efficiency we have, efficiency is equal to P sub g minus loss all over P sub g times 100%. Using the values we have, efficiency is equal to 4,880 minus 512 all over 4,880 times 100%. That will result in 89.5%. Okay, for the last example. A 250-volt generator supplies power to loads of A and B. I sub 1 being 160 amperes and I sub 2 being 140 amperes. A pair of wire each 0.1 ohms connect the generator terminals to those of load A. Another pair of similar conductors, each 0.1 ohms connect the A and B loads. Finally, a third pair of wires, called feeders, each 0.5 ohms joins the generator and load B terminals. Determine the voltage at load A and B. So guys, this circuit can be simplified like this. And also guys, you have to understand that the total delivered current by the generator will be I sub 1 and I sub 2, which is equal to 160 amperes plus 140 amperes that result in 300 amperes. Simply take junction D, which I sub G is equal to I sub 1 plus I sub 2. So the solution guys, will be like this. Take a look at the circuit flowing here is I sub 1. And here will be 300 minus I sub 1. And while here is I sub 1 minus 160. Since load currents are already given. So now we take the loop ABCDA. 250 minus 0.2 I sub 1 minus V sub A, equal to 0, or it can be written as 250 minus 0.2 I sub 1 equals V sub A, which will be our equation number 1. Then take the loop ABEFCDA. 250 minus 0.1 times quantity 300 minus I sub 1 plus 0.2 times quantity I sub 1 minus 160 minus V sub A, equal to 0. 250 minus 30 plus 0.1 I sub 1 plus 0.2 I sub 1 minus 32 minus V sub A, equal to 0. So 188 plus 0.3 I sub 1 minus V sub A, equal to 0. 188 plus 0.3 I sub 1 is equal V sub A, which will be our equation number 2. Using the equations number 1 and 2. 250 minus 0.2 I sub 1 is equal to 188 plus 0.3 I sub 1. 250 minus 188 is equal to 0.3 I sub 1 plus 0.2 I sub 1. So 62 is equal to 0.5 I sub 1. I sub 1 is equal to 62 divided by 0.5, that will be equal to 124 amperes. Then I sub 2 is equal to 124 minus 160, that will result in negative 36 amperes. The negative sign of I sub 2 indicates that the direction of the current should be from F to C, not C to F. Using the value of I sub 1 and equation number 1. 250 minus 0.2 times 124 is equal to V sub A. So V sub A is equal to 225.2 volts. And V sub B is equal to V sub A minus 0.2 I sub 2. 225.2 minus 0.2 times negative 36. That will result in 232.4 volts.
Hey guys, thank you for watching. See you on my next vlog. Please don't forget to like, share, and subscribe for more videos.